We're looking at graphing rational functions today. This is actually a very long and involved process, and we need to make sure we understand each step because, in all honesty, each step really isn't that difficult. It's just there's multiple steps, and it's easy to mess one up. We're going to take an example of a function f of x equals 2x over x squared minus 4. And all we're going to be using are the processes and the procedures and all that we've learned before. We're really starting to build on ourselves. The first one when we look at a rational function is to determine any symmetry. Now if you remember, the two types of symmetry we have symmetry about the y-axis for even functions and symmetry about the origin for odd functions. And the way to determine symmetry is to take your original function, which in this case is f of x equals 2x over the quantity x squared minus 4, and we plug in negative x for x. So f of negative x gives us 2 times negative x over negative x squared minus 4, and we reduce it, we wind up with negative 2x over x squared minus 4. So basically the only thing that changed was this negative in the numerator, and we can actually bring that out front. So we have negative times 2x over x squared minus 4. Notice that 2x over x squared minus 4, that's our original function. So that gives us negative f of x. So we get f of negative x is negative f of x. This is an odd function. Therefore, we know this graph is going to be symmetrical about the origin. So if we take the graph and we rotate it 180 degrees, we wind up with the exact same graph. That should give us an idea and help us out as we go to plot points and we go to actually graph it, whether we know we're on the right track or not. The second thing we want to do is find out the y-intercept. If you remember, by definition, the y-intercept is always where x equals 0. So we take our original function again, f of x, which is 2x over x squared minus 4, and we plug in 0 for our x's, and that basically gives us 0 over negative 4, which is 0. So the y-intercept is 0, 0. Now the next thing to do is find the x-intercepts. Now by definition, the x-intercept is where y equals 0. So what we do is we set our function equal to 0. So we get 0 equals 2x over x squared minus 4. Well, for a fraction to be equal to 0, the numerator has to be equal to 0. We don't worry about the denominator. So in this case, all we do is we take the numerator and set it equal to 0. We get 0 equals 2x, or x equals 0. So the only x-intercept we have, again, is 0, 0. So our only x-intercept and our only y-intercept are 0 and 0. The fourth step is to find our vertical asymptotes. Well, to find vertical asymptotes, we are concerned about the denominator. We want to know when the denominator equals 0, because when the denominator equals 0, the function's undefined. So we set our denominator, which is x squared minus 4, set it equal to 0, and that gives us x minus 2 times x plus 2 is 0. And if we solve each one of these, we will find that we have vertical asymptotes at x equals 2 and x equals negative 2. Those are formulas for vertical lines, so those are going to appear in our graph. Our next one is to find the horizontal asymptote. This one is actually easy to do, but kind of tricky at the same time, because we're not really solving for anything as much as we're observing the function. Our function was f of x is 2x over x squared minus 4. The degree of my denominator is 2. To find degree, we look at the exponents, and the largest exponent is 2. So we look at the exponent of the variables, and the largest exponent is 2, so the denominator has degree 2. The numerator, the exponent is understood to be 1, so it is degree 1. So if the degree of the denominator is greater than the degree of the numerator, that means there's a horizontal asymptote at y equals 0, or the x-axis. Next thing we have to look at is we got to look out for points where our behavior may change. And those are basically our x-intercepts and our vertical asymptotes. So our x-intercept was 0, and our vertical asymptotes were negative 2 and 2. So we're going to look around these points. I'm going to plug in some points. I just chose negative 2.5, negative 1.5, negative 1, negative 0.5, 0.5, 1, 1.5, and 2.5 as my x values. I'm trying to get an idea for the behavior of the graph. And I used a calculator to calculate these. And if you'll notice, my negative 2.5 gave me negative 2.22, and my positive 2.5 gave me a positive 2.22, which makes sense because we said negative f of x was the same as f of negative x, so my signs should change when I plug in the opposites. And if I'm going to plot these points, here are my plots. It gives us a good idea of what happens around the origin here and around my vertical asymptotes. Now, I have a graphing utility which doesn't let me do vertical asymptotes, so I apologize for that. But imagine these vertical lines coming up and down at -2 and at +2. And really, what happens on vertical asymptotes, one of two things happen. Either the graph shoots up to positive infinity or it shoots down to negative infinity. So when I'm looking right to the left and right of my vertical asymptotes, I'm trying to get an idea for which direction this is heading in. And then to the right of 2, I plugged in 2.5. I got out 2.2, so that tells me it's heading up. And to the left of 2, I plugged in 1.5 and got -1.7, so that tells me it's heading down. Also notice the horizontal asymptote was at 0. Now this does cross the horizontal asymptote. The horizontal asymptotes, we care about end behaviors. What happens as we go to infinity and negative infinity. And notice on my graph, as we head towards infinity and negative infinity, this graph of this function gets closer and closer towards the x-axis. Again, I don't think we did anything that earth-shattering in any one of these steps, but there's a lot of steps involved. Please practice these. These are going to take probably doing about 10 of these problems to get really proficient at it, so make sure you understand what's going on. Let me know if you have any questions.